Hello friends, welcome to Physics with Ben. Don't forget to subscribe, like, comment and share this video that you are watching. You may also love to turn on the notification bell so that you can get due notification anytime I upload a new content. You may also love to click in the description on this video that you're watching to get the learning resource material on frictional force. Without wasting more time, let us go straight to the business of the day. We have a brand new topic before us today, frictional force. Before we proceed, let us look at the learning objectives. By the end of this class, you are supposed to know how to define frictional force. You are supposed to know how to list and explain the various types of frictional force. You're also supposed to state and explain the laws of solid friction. You're also expected to define the coefficient of static friction. You are also expected to determine the coefficient of friction using various surfaces. And lastly, you are also expected to do a whole lot of simple calculations. Without wasting much time, let us go straight to the business of the day. First up, what is force? In our previous class, in our videos on motion, I have explained what force is. But because of this class, for the sake of this class, I'll have to do a quick revision and a recap on what frictional force is. Sorry, what force is. So what is force? Force is defined as a push or a pull on an object. It is measured in the SI units of Newton. So it means that without force, there is no motion. Force is a very, very important concept in the study of physics and physical science in general. There are two main types of forces. We have the contact force and then the force field. The contact force are those forces that require a physical contact on the objects with which they act upon. If I exert a push force and a pull force here, that is an example of contact force. Another example is pressure. Another example is tension, strain, stress. They are all examples of contact forces. The other forces are called the non-contact force or the force field. These forces do not require a physical contact on the object with which they act upon. Their action and effect are felt at a distance. Examples of non-contact forces are the gravitational force, the magnetic force, and the electrostatic force. So frictional force is an example of contact force. So what is frictional force? Frictional force is defined as a force that opposes the relative motion between any two surfaces that are in contact with each other. There can be solid friction and fluid friction. For the sake of today's class, what we are looking at today is a solid frictional force. For the fluid friction, we talk of viscosity. We're going to make a video on that. Fluid at rest and in motion. Frictional force is a force of opposition, and it acts whenever there is motion or tendency for something to move. Hence, friction force is absent if there is no motion or if there is no force intending to cause motion. It stops your car when the brakes are applied. That is, when the force producing this motion is withdrawn. Friction slows down the body until it eventually comes to rest. It also prevents your foot from slipping backward when you are walking. We want to look at types of frictional force. Types of frictional force. There are two main types of frictional force, namely, we have the static or limiting frictional force. The static or limiting frictional force, when the body is at rest, resting against another body, just as you can see here. A perfect example of static or limiting frictional force. And then we have the other one, the dynamic or kinetic friction, when an object is sliding over another object, as you can see me doing it right now. So let's look at their proper definition. The static friction or limiting friction, this is the frictional force that exists between two surfaces relatively at rest and preventing the motion of one surface over the other. It is also the maximum force that must be overcome before a body can just start to move over another body. Dynamic friction or kinetic friction. This is the frictional force that exists between the two objects that are in relative motion to each other. It is also a force that must be overcome before a body can move with uniform speed over another body. Next up, we want to look at the laws of solid friction. Very, very important. The laws of solid friction. There are 5 main laws of solid friction, and this law states as follows. Number 1, friction opposes the relative motion between two surfaces in contact. The first law looks like the definition for friction. It acts in a direction opposite to that of the motion. What is this law trying to say? It means that if I push these objects this way, the frictional force will act this way. That is the meaning of the first law. The second law, the frictional force increases with the force which tends to start the motion. Law number 3, frictional force is dependent on the nature of the surface in contact. What law number 3 means is this, that if the surface is smooth, frictional force will be less, and if the surface is rough, frictional force will be high. Law number 4, frictional force is independent on the area of the surface in contact. I say that again. Frictional force is independent on the area of the surface in contact. What this law means is this, that if the area of the surfaces in contact is wide, frictional force will still exist. If the area is as tiny as the amount of this pen on this board, frictional force will still exist. Law number 5. Law number 5 states that frictional force is directly proportional to the normal reaction. Law number 5 introduces us to the first equation in frictional force. It states mathematically as frictional force is directly proportional to the normal reaction. We can call this equation star. And removing the sign of proportionality, we write that our frictional force is equals to mu r. We can call this equation number 1, where F is the frictional force measured in the SI units of Newton, and mu is called the coefficient of static friction with no SI unit. It is a dimensionless quantity. while R is called the normal reaction that is dependent on the mass of the object. It is also measured in the SI units of Newton. So if we make mu the subject formula, we're going to have a brand new equation as this. Mu is equals to force all over normal reaction. And we can call this our equation number 2. Dimensionally, force is measured in the SI units of Newton, and the normal reaction, I also said, is dependent on the mass of the object, and it is also measured in the SI unit of Newton. So if Newton cancels out Newton, then we have no SI unit left. So for this reason, we say that the normal reaction is a dimensionless quantity. So we call this our equation number 2. Next up, we want to look at the real definition for the coefficient of friction. The definition for the coefficient of friction. From the board, from equation number 2, we can define the coefficient of static friction as the ratio of the frictional force to the normal reaction, as simple as that. And mathematically, you write that mu is equal to F over R with no SI units. So what this means is that the coefficient of friction and the normal reaction, they are inversely proportional to each other. And the frictional force and the coefficients of friction, they are also directly proportional to each other. What this means is that if the normal reaction increases, the coefficient of static friction will decrease. So if you increase the mass of the objects, you know that normal reaction is equal to mass times gravity. We're going to look into that in this video as we proceed. So increase in normal reaction will cause a decrease in the coefficient of friction, and increase here will cause a decrease here, and decrease here will cause an increase here. And here is increase. Increase in the frictional force will cause the coefficient of friction to also increase. That is the meaning of that. So next up, we want to look at the most important aspects of this topic. Stay tuned and watch to the end. We want to look at determination. Determination of the coefficients of friction. I want you, whatever you are doing, we have come to the most important part of this video. I'd like you to activate your senses as you watch. There are various methods the coefficient of friction can be determined. There are 5 of those methods that I highlight in this video. First up, we have the horizontal plane surface with horizontal pull force method. I write method 1. Okay, let me write it. Number 1, the first method, number 1. Using the method of the horizontal plane surface, the horizontal plane surface with horizontal pull force weights. Horizontal pull force. I said there are 5 methods. So first off, we have the horizontal plane surface with horizontal pull force method. Good. So what is this method all about? I will draw something here quickly. Let's suppose that this is our horizontal surface. And this is a symbol for surface in physics. And just what I'm doing here right now, just on the board. This is the first method. Horizontal plane surface with horizontal pull force. Pull or push force. It could be pull or a push force. So this is the method I am discussing right now. So this block, if you weigh it in the lab, the block weighs 230 something grams. This is 235 grams. That is the mass of the block. So if you put this block of wood here, there at the center down here, there is the weight of the block, and that weight is equals to mass times gravity. And up here, from here up, is the normal reaction. And then here, if I pull this object this way, I drag it this way, that is my FP, my pull force. I write it as my FP, my pull force. So as I was saying from the intro of the class, if you pull this object this way, since frictional force is a force that opposes motion, the frictional force will act this way. The frictional force will act backward. So I write F frictional force. I write F subscript F here. Or let me say friction of, F subscript F, my frictional force. And then the coefficient of friction, it is in between this block. It is in between this block and this surface. So that's our mu. So we are looking for our mu. So from here we can generate all the equations that will be used for calculations. So first off, we write the first equation for friction. Our frictional force is given to be mu times normal reaction. We know this as our equation number 1. Right? Good. Now from this geometry, there's something I want us to understand. There's a topic in physics called addition and subtraction of vectors. We said in that topic that vectors are added and subtracted using geometrical method. What those rules are saying is that if vectors are acting in the same direction, you add them up. If vectors are acting in opposite direction, you subtract them. If vectors are acting at right angle with each other, you apply Pythagoras theorem. If vectors are acting at obtuse or acute angle, you all apply the sine rule and the cosine rule. So force is a vector with both magnitude and direction. So in this geometry, I'll be drawing on the board and explaining here. You must keep that in front of your mind, not at the back of your mind. So we're going to treat frictional force as a vector quantity. You get it? Good. So this force is equal to this force. And this force is also equal to what? This force. But that is not what we are going to write right now. First off, if this object tends to move this way, then it means that this force is greater than this force. So the first thing we are going to do is to find the net force in this direction. So we'll write that our net force Fn, is given to be this force minus this force, because this object is moving in this direction. So we'll write that the pull force, which is Fp, minus the frictional force Ff. So we call this our equation number 2. There are moments examiners may ask you to calculate the net force. This is how to go about it. For this type of arrangement, this method, this is how you go about it. Next up, we want to equate the normal reaction with this. So we are free to write that the normal reaction R is equals to the weight. And the normal reaction R is also equals to the mass times gravity. It is for this reason that the normal reaction also shares the same SI unit with weight, friction, Newton, and then from here you have mu with no SI units. So these are the basic equations that you will need here. And the remaining equations can be gotten using what I call the physics of cut and join. The physics of cut and join. So from here we can still write that net force FF is equals to what? Is equals to the pull force minus mu R. So you can make mu the subject of the formula by writing that your mu R is equals to frictional force minus the pull force. So you divide both sides by R, and then your mu is equals to the frictional force minus the pull force divided by the normal reaction. So in any case, you make mu the subject of the formula and then you substitute. From here we can still bring in from here we can still write that this equation 3, equation 4, equation 5, and this is equation 6. We can still derive another equation by writing. We know that R from here, R is what? R is equals to frictional force all over mu, and that will give us what? So we are free to write that frictional force all over mu is equals to mass times gravity. So you also make mu the solid formula, and then this is our question number 7. So this is how we can find the coefficient of static friction using the horizontal plane force. The horizontal plane surface with horizontal pull or push force method. In the next video, we're going to make use of all of these equations to solve some beautiful questions. Next up, the next method we want to look at is the horizontal plane surface with inclined pull force method. The horizontal plane surface with inclined pull force method. That is method number 2. What is this method talking about? This method is talking about something like this. You have something like this. And then the object is resting on. This is the mass, and this is the surface. So the weight is down. W is equals to mass times gravity. The normal reaction always in this direction, and that is your R. And you know that from F is equals to mu R. You know that your R is equals to F over mu. So this is F all over mu. So if you pull this at this angle, know that the frictional force will also act this way. So this is your FF, frictional force. So if you pull this way, there are two forces acting in this direction. Up here is the Fy component of this force, and somewhere here is the Fx component of this force, and here becomes the resultant force in this direction. So good. This is what I'm trying to say. So you have, and this force is having this angle theta, and this force having this angle theta. If you remember what I said in addition of vectors, you will start applying that here, and then we have this thing resolved. So let us generate the equation for this set of arrangements. First off, we have the resultant horizontal frictional force. The resultant horizontal frictional force. We have here our frictional force FF to be equals to Fx. Knowing that our frictional force is equals to mu r, that's established. So our Fx, the forces in the horizontal, is given to be what? F cos theta. Good. So from this equation, we can still, this is always our equation number one. We can still establish that mu r is equals to F cos theta. So this is our equation number 2 here, and this is our equation number 3, and this is our equation number 4. Good. Now let us look at the vertical, the resultant vertical friction forces. Good. Now it will interest you to know that there are two forces up here. We have the normal reaction, we have the Fy, and this Fy is the same thing as what? F sin theta, and Fx is the same thing as what? F cos theta. So the normal reaction, what we have here is the downward weight is equals to the normal reaction plus Fy. We can call this equation number 5. Substituting every variable correctly, our W is mg, so rather mg is equals to R. R is F all over normal coefficient of static friction, and Fy is F sine theta, so right, plus F sine theta. So we can call this equation number 6. Good. So there are situations where they will ask you to find the tension created in the string. What you are seeing here is something very, very simple as this. This is what you are seeing. If I decide to drag this object like this, that's exactly what you are seeing. The first one, I drag it horizontally. I drag it this way. And this one, you have to drag it like this. Those days when you used to play with toys, you tie a rope and you drag a motor toy on the road. That is exactly what happens. So there's a tension created. There's a tension created in this string. And this force is the same thing as this tension. And that tension is the resultant force. So they may ask you to find this tension in the spring or in the string. So this is the summary of the equations that you will need when using this method to find the coefficient of static friction. So you can from here can make mu the subject of the formula, and then you find the coefficient of static friction. Next up, we want to look at number 3, the horizontal plane surface with smooth pulled force method. Horizontal plane surface with smooth pull method. Let me write it this way. That's number 3. Method. Good. What is this method talking about? This method is very, very simple as well. And we look at it, and I draw something like this as my plane surface, and then so if I have an object here, good, as my mass as usual. So up here my normal reaction, and if I put a groove here, let me take it down a little bit, and then good. So this is a platform. So if I pull this way, the frictional force will act this way. So my F frictional force is here, and here is my pull force, which is the same thing as the tension in the string. So up here is my normal reaction. So if I attach some weight down here, the weight that will overcome this load and start sliding, there's going to be a tension created also here down and an arrow up here. Good. So this is a body of mass, that, and then this is my weight acting in this direction. This is my weight acting in this direction. Mass times gravity. So I'm gonna have it's exactly what I have here, but now in a different way. So my total horizontal frictional force, I write horizontal components of this force will be given as, I'm going to find my total this, which is the object is moving this way, which means that this mass has overcome this weight. But something will happen, they will move simultaneously. They will move simultaneously. Something like this. And so, such questions you end up solving them using simultaneous linear equation, and which is what I want to derive right now. So here what you have is this. Your total horizontal force or net force, your total net pull force or horizontal force is given since this force has overcome the frictional force. It means that this force is greater than this force. And so your total net pull force or net force in this horizontal direction become this pull force minus this frictional force. So we write that our net force, let me write again, horizontal net force, good, our horizontal net force becomes our pull force, or in this case, our tension, good. Tension minus the frictional force. Knowing that our frictional force is always equal to mu r, and this force gives an acceleration, and that is mass times acceleration. The mass of this object times the acceleration of the force we give. So we're going to write that our mass times acceleration is equal to this tension minus mu r. So we call this equation number 1 always, and this is our equation number 2, and this is our equation number 3. Now we look at the total vertical components of this force. Vertical components of this force. The vertical component of this force is given as this. This is it here. So this is the total vertical net force. So there's a tension created here. So we write that FVN, total vertical net force, is equals to this weight. Of course, the weight is greater than the tension, and they are acting in opposite direction. So this weight is a force, this force minus this force. So we write that this weight minus this tension. And it will interest you to know that we have nothing like T tension 1, tension 2. Because the tension created here is still the same tension created here. Just as these bodies, the masses are not the same. So they will move simultaneously. So we write that also this is also an acceleration. Mass times acceleration. So we write that our mass times acceleration is equals to mass times gravity minus this tension. So we call this equation number 4. So equation number 3 and equation number 4 are the two physical simultaneous equations you can use to solve questions on things like this. When you see a question coming from this direction, this is how to go about it. We're going to make another video where we are going to make use of all of these equations to solve a whole lot of simple equations. We are looking at the other part, the fourth method of the plane surface method. Good. The inclined plane surface method, very, very interesting method. I'll just analogize that quickly. It's simply tilting of this guy like this. See that? Good. So let me draw the diagram quickly. If this is my horizontal good. This is a block of wood of mass n. A block of wood of mass n. So there's an inclined plane here. And as we said, if you increase the angle, you are going to increase the chances of this guy to slide down. So what happens here is that when increase in the angle decreases the frictional force. The frictional force is overcome when the angle of inclination is increased. So what are the equations controlling this? The geometry behind this. So there are two ways this can happen. When the object slides down naturally by you increasing the angle of inclination to the horizontal surface, or by you pulling it up. So let's do it as though the object is sliding down naturally. So if the object will slide down naturally, or it will push down, or the angle will be increased so that it slides down, then this is what we have. The frictional force will act this way. Why? Because the direction of the motion of the object is this direction. The frictional force will act this way. So write that our frictional force F, small f, is there. Because friction will always act in the opposite direction to where the object is moving. So in this case, the object will, since the object is inclined at a plane from the knowledge of addition of vectors, the object will have something like this. We call this our Wx. That is the horizontal component of the weight, Wx. And up here will be the normal reaction. The normal reaction R. Mind you, from here to here is the same as from here to here. The direction, the arrow indicates the direction of the vector, while the length of the line indicates the magnitude of the vector. So since the horizontal component of this weight is equals to the normal reaction, then the arrows must be the same. That is the wisdom behind what I just drew here right now. Now, down here will be the what? The vertical component, W, Y, the vertical component of that. And if I draw something like this, good, this becomes just W, the resultant weight. I didn't draw it perfectly, but it is something that looks like this. You have your WY, you have your WX, and here becomes what? Your W. This is what I tried to draw here. You cannot decode it. This is what I just drew here right now. This is it here. So here is the resultant weight. Now, this is the same thing as W cos theta. And from here, this is the same thing as mu R. You can use these diagrams to generate all the equations that you are looking for. And here is W sine theta. And from here, you know that your mu is equal to your normal reaction is equal to the frictional force divided by that. So let us generate our equations now. So from here we write that frictional force is equal to mu R. We call this equation number 1 always. And then we also write that the horizontal component of this is equal to that. So we write that Wx is equal to that. That becomes our equation number 2. By substituting the values of this, we write that W cos theta, W cos theta is equal to F all over mu. You can call this your equation. So we also want to write that this is equal to this. So we write that Wy is equal to the frictional force. So we substitute again by writing that W sine theta is equal to the mu is equal to mu R. You can call this your equation number 4, and you can call this your equation number 5. If you continue to go on and on and on again, you can generate more of the equations. These are the basic equations that can be used here. This is the horizontal component. If you can still move on, you can still write that this equation is congruent to W means mg, right? This is the same thing as mass times gravity. So write that mass times gravity cos theta is equal to F all over mu. So we can still write again that here this is congruent to mass times gravity sine theta is equal to mu R. So you make mu the subject of the formula, and then you find the coefficient of friction on this particular surface. Still on this surface, what happens then when the object is pulled in the upward direction? This is what happens. Watch out. Now, I'm going to reverse this. If the object is pulled this way, this is what you have. If the object is pulled this way, the whole arrangement remains the same, but this is what will happen. Here you now have your pull force here. Your pull force, and then the frictional force will act in this direction. So this is, let me write this way. This is your frictional force. This is your frictional force, F is with F, and this is your what? The vertical component of the weight. So here, what do you write now? This frictional force, this pull force is equal to what? This. Now, I forgot something in the other diagram. That is the net force in this direction. So I write that my net force here, since this pull force, I always know that pull force is equal to mass times acceleration. That is what you must always know. This pull force is always equal to what? Mass times acceleration. I did not bring the pull force here the other time because it was sliding down naturally. So that is that. So the net force here becomes this pull force minus what? Minus the frictional force plus, let me put it inside the brackets, minus brackets the frictional force plus the vertical component of this. So we write that our frictional force is always equal to mu r. So the net force in this direction in pulling that object up is this pull force minus this force and this force. So we call this equation number 1, we call this equation number 2. And if you substitute correctly, we have that our net force here is equal to mass times acceleration minus bracket frictional force mu r plus W. We know that this is the same thing as what? W sine theta. We call this equation number 3. Good. So if we continue to move on, we are going also to write that this force is equal to this force. It's another equation. So we write that the frictional force, the pull force, is also equal to the frictional force, plus Wy. Yes. So we write again that mass times acceleration is equal to mu r plus W sine theta. Yes, W sine theta. While everything still remains the what? We write that, and if you want, you can make W the subject of the formula to find the vertical component of the weight. Then we also write that Wx remains the same thing as your R. So you can call this your equation number 4 and call this your equation number 5. And also call this your equation number 6. So this is what happens when the force pulls the object this way. We also use something like this to solve questions under simple machines inclined plane. Last but not the least, we are going to look at inclined plane surface with smooth pulling. And I think I have to clean that. Let me clean this. Let's suppose you have a groove here, and then you have an object here. Then you try to good. So you attach a weight here. So this is weight. up here is your normal reaction, and then down here is this your Wx, and this is your W, and then here is your W y. It's an angle of inclination here. Here is the tension is here. The object is moving this direction. So this pull force is the same thing as the tension. And here there is a tension created down here and up here. So there's the total downward movement. And this is the same thing as, and this tension here is also the same thing as the pull force down here. And this is the same thing as mass times acceleration. And this is the same thing as mass times acceleration. So to derive the equation, what we have here is this. We have the total net force, the total the total inclined, the total inclined net force becomes, that is inclined net force. In, inclined net force, is equals to this tension. The tension has overcome this weight, that is why it is moving up. So this tension created here minus this weight. So we have T minus W y. I forgot something. Since it is moving up here, the frictional force will act in this direction. So we have also here, in addition, we have in addition the frictional force. The frictional force will act in this direction. That is your F. The frictional force will act in this direction. So this pull force has overcome the vertical weight of this object and the frictional force. That is why it is dragging it up here. And again, this guy and this guy will move simultaneously, just as what you have on horizontal plane surface with smooth pulley. It's the same thing you have here. Here too, you also solve it using simultaneous equations. This object and this object will move simultaneously. And the tension here is also the same thing as the tension here. Is that understood? Good. So what we have here is that the net force here becomes this pull force minus bracket this plus the frictional force. Remember that our F is equals to mu R is always the equation number 1, and this is number 2 in this case. So if we substitute correctly, we have here as our mass times acceleration is equals to the tension here minus bracket W sine theta plus mu R plus mu R. We call this equation number 3. Now we are done with the inclined net force at this angle. Now let's look at the downward force. What do we have here? There's a tension here, and that tension is equal to this. That tension is equal to this. So we write that our total downward dn, downward net force, here is equal to this weight minus this tension. This weight minus this tension. We call this our equation number 4. So we have it that since this is also to mass acceleration, we call the mass of this times acceleration is equal to this weight, which is mass times gravity times the tension. We call it equation number 5. You can do what I call the fields of cut and join. This is mass, that's gravity. This is W cos theta, and this is W sin theta. You can do what I call the fields of cut and join and generate more of these equations. With this, we have come to the end of this video. Next up, in our next video, we are going to use all of these equations to solve a whole lot of calculations. Don't forget to subscribe, like, comment, and share this video. Thank you. God bless you. Bye-bye.